Hey everyone. So starting from today, for the next couple of hours, we are going to talk about the transportation and assignment problems. And these two problems, transportation problem and assignment problems, are very well studied traditional examples of the linear programming problems. And most of the operations research textbook includes these two problems as the prototype of the LP model. So, okay, then first, let's talk about transportation problem. So let me first share my screen. Okay. Okay. Okay, so the transportation problem, just to let you know, received this name because many of its real-world applications involves the determining how to optimally transport the shipments. But some of the its important real-world applications actually have nothing to do with transportation. Okay, so, okay, this one. So first, what did they say? The standard scenario where the transportation problem arises is that you want to send sets of shipments from some sources to destinations. And each source has a given supply, and each destination has a given demand amount. And each road that connects the source destination pair has a given transportation cost per unit of shipment. Okay. So this screen shows a prototype transportation problem with three sources here. Those are the supply nodes, and four destinations. Okay, those are the demand nodes for the flow, and also it has some associated shipping cost. Okay. And the goal of the transportation problem is to find the least cost way of transporting the goods from the sources to destinations. Of course, while at the same time satisfying the customer's demand in the destination without exceeding the available supply amount at the sources. Okay. And problems with this structure arise in many different real-world applications. Okay, so this screen shows a similar situation with the same number of sources and destinations for the flow. And this time, we consider a situation that could arise in the power companies, the power distributions plan. Okay. And this figure also includes the shipping costs, supply amount, and demand amounts for a power company. Okay. And the power company has these three electric power plants, right? Plant number 1, 2, and 3, right? And that supply the needs of 4 different cities, right? And plant number 1, for example, can supply 35 million kilowatts per hour, and plant number 2 can supply 50 million kilowatts per hour, and plant number 3 is 40 million kilowatts per hour. And the peak power demands in city number 1, which occurs at the same time, is going to be 45 million kilowatts per hour. And in city number 2, that's going to be 20 million kilowatt. City number 3 would be 30, and city number 4 would be another 30 million kilowatts. Okay, and the cost of sending 1 million kilowatt of electricity from each plant to city depends on the actual distance, travel distance that the electricity must travel. Okay, and those are included on each arrow, like 8, 9, 14, 6, 12, 9, 10, 13, 16, and 9, 7, 5, like that. Okay. Okay. Then given the information, we can make a nice table, a transportation table like this, that summarize all of the critical information, right? So here I have listed sources in each row, right? Those are the 3 different sources, plants number 1, 2, and 3, and the destination in each column, okay? So we have 4 different destinations. Those are the 4 different cities, right? And it also includes the shipping cost from each source, each plant to each city, okay? And the customer's demand and the available supply amount for a power company, like that, okay? And we'd like to find the least cost shipments that will satisfy the given requirements using the available supplies, okay? So truly, this is one of the optimization model, right? Optimization problem. And the optimization problem is a computational problem that the objective is to find the best of all the possible solutions, right? And when you deal with it, first, you need to define the problem of interest, right? And once the optimization problem is defined in words, the next phase is to reformulate this problem in a form that is convenient for analysis, okay? And the conventional operations research approach for doing this is to construct a math model that represents the essence of the problem. And we've learned that mathematical model consists of decision variables, the objective functions, and some constraints, right? And we also talked about how to construct the linear programming model, right? So linear programming model is a typical mathematical model where both objective function and all of the constraints are linear functions, right? Okay, and the first thing, we need to define the decision variable, right? Decision variable is a number of variables whose values are to be determined. So these are what you want to know and what you must determine within your LP model, right? So in our case, we could define a variable for each decision that the power company must make, because the power company must determine how much power is sent from each plant to each city. We define X variable. So X variable has 2 subscripts. that represents number of million kilowatts produced at plant number I and sent to plant number J. Okay. And our objective function, that is the in general the measure of performance expressed as a function of the decision variable, right? So in our case, we want to minimize the total shipping cost or minimize the total travel distance, right? And here, the cost of supplying the peak power demands from plant number 1 to each city is going to be 8 times x11, right? Plus 6 times x12 plus 10 times x13 plus 9 times x14. So the total cost of supplying the peak power demands to each city may be written as, so this is the cost of shipping the plant power from plant number 1, right? And you also need to add, let me see if I have this. No, I didn't. Okay, so you have to add 9 times x21 plus 12 times x22, right? Plus 13 times x23 plus 7 times x24, right? So that's the cost of shipping the power from plant number 2, right? This part. And you also need to add the cost of shipping the power from plant number 3. That's going to be using this row from the table row, 14 times x31 plus 9 times x32 plus 16 times x33 plus 5 times x34, right? And you want to minimize all of this, right? So that's going to be our objective function of minimizing the total transportation cost. Okay, the next is considering the constraints. So that's the restrictions on the values that can be assigned to each decision variable, right? So in our case, the power company faces 2 types of constraints. The first, the total power supplied by each plant cannot exceed the plant's capacity, right? For example, the total amount of power sent from plant number 1 to the 4 cities cannot exceed the plant's capacity of 35 million kilowatts, right? So we need to put 35 on the right-hand side value, and this value has to be greater than or equal to the summation of all of these, right? x11, x12, x13, and x14, right? Okay. Of course, here in this first constraint, the first subscript of each variable here, first subscript of 1 represents the shipment of the power from plant number 1, right? Okay, and in a similar way, we can also find the constraints, the plant number 2 and plant number 3's capacities, right? So let me write it down up here. So for the plant number 2, it's going to be x21 plus x22 plus x23 plus x24, right? Has to be less than or equal to the capacity of the plant number 2, which is 50 million kilowatts, right? Likewise, for plant number 3, you can have x31 plus 32 plus 33 plus 34 has to be less than or equal to 40, right? So these 3 constraints are what is called the what is that? The supply constraint. Okay, because it simply say that no more shipments, no more is shipped from each supply, right? Each supply, the location, and that is available. So that is called the supply constraint. Okay. Next constraint is what we call the demand constraint. That ensures that each city will receive the enough amount of power, sufficient power to meet its peak demand. Because each city demands power, each is a demand point, right? So that is called demand constraints. So what is that? The city number 1, for example, must receive at least 45 million kilowatts, right? Here. So we have right-hand side value of 45, but the left-hand side must be greater than or equal to this amount. Okay. So again, in this constraint, this time the second subscript, the value of 1, represents the shipment of power to city number 1. Okay. Similarly, we obtain a constraint for each of cities number 2, 3, and 4. Right. So for city number 2, we are going to have x12, right, plus x22, x32, right, has to be greater than or equal to the demand amount as city number 2, which is 20 million kilowatt, right? For city number 3, it's got to be 13, 23, 33, right? Has to be greater than equal to 30. Likewise, for city number 4, it's going to be x14 plus x24 plus x34 has to be greater than equal to 30, which is from here. Okay. So again, these are called demand constraint. Because it ensures the location the city receives is peak demand amount. Okay. And of course, all of the x variable must be non-negative So we add the sign constraints, sign restrictions, x of ij has to be greater than or equal to 0 for all of I and j values. Okay. So, okay, I have this. Okay, let me move this. Okay, or let me just disable this. Okay, so here, combining all together here, this is the complete LP model for our transportation example. Okay. Sorry, let me. Besides this, so this is better. Okay. Okay. So the first set of constraints are the supply constraint, right? And second set of constraints are demand constraint. And in general, a transportation problem is specified with the following information. So usually the first subscript, the index I represents the sources, and J, the second subscript of the decision variable, represents the destinations. And M is the number of sources, N is the number of destinations. And S of I stands for the quantity of goods available as source number I. DJ is the quantity of the shipments or goods required at each destination J. And C sub ij is the unique cost of shipping the goods from source, each source to destination. And we are required to find the decision variable x of ij, that is the quantity of the shipments from each source to destination. Okay. And this is the general format, the LP format of the transportation problem. So again, the first set of constraints are the supply constraint. And second set of constraints are demand constraint. Okay. Okay. Let's see. Okay, I included this screen just tell you some key characteristics of the transportation problem. Actually, the real-world applications of the transportation problem tends to require a very large number of constraints and variables. So a straightforward computer applications may require a huge the amount of computational time. But fortunately, there is a key characteristics of this transportation problem. Is that the most of the coefficients in the constraint sets are 0, and the relatively fewer the non-zero coefficients appear in a distinctive patterns like this. Okay, and the objective function is gonna be mostly it has the non-zero coefficient, but in the constraint set, especially for the supply constraints, we have a distinct pattern of non-zero coefficients for the demand constraint, like this way. Okay, so as a result, it has been possible to develop what he called the transportation simplex method, which is a streamlined version of the ordinary simplex method for effectively solving the transportation problem. Okay, but I didn't include the transportation simplex algorithm in these new recordings. But let me know if you are interested in that. Then I will definitely share the web link to my old lecture videos that does include the both the ordinary simplex algorithm and the transportation simplex algorithm as well. Okay. Okay, then now let's move on to our example problems. Okay. Okay, so in this example, the manufacturing company has 3 plants producing child push chairs that are to be shipped to 4 distribution centers. And plants number 1, 2, and 3 produce 12, 17, and 11 shipments per month, respectively. And each distribution center needs to receive 10 shipments per month. And the distance from each plant to the respective distributing centers is given in this table. And the freight cost for each shipment is $100 plus 50 cents per mile. Okay, so $100 would be the fixed cost, and the 50 cents would be the variable cost, right? And then we'd like to know how much should be shipped from each plant to each of the distribution centers to minimize the total shipping cost. Okay. Okay, so I've extracted this example problem from the one of the operations research textbook by Hillier and Lieberman. Okay, then let's solve this problem. So let me split this screen in half. And I'm gonna open up Microsoft Word. Okay. Okay. And let me zoom in a little bit. Okay. So it's a little better. But let me zoom in a little bit more. No, it's too much. Okay, so let's just go with this. Okay, so first, let's formulate this problem as a transportation problem by constructing the appropriate parameter tables. Okay. So I'm talking about like this table, okay? So this table is called the transportation table, okay? That does include the demand amount and supply amount from each destination and sources, right? Like this. Also, it does include the unit transportation cost from each sources to destinations, okay? So we are going to build similar transportation table for our example. Okay. So first, let me get something like this. Okay. So I'm gonna put the plant in here. It's plant number 1, plant number 2, and plant number 3. Okay. And I'm gonna put the destination up here. So that's gonna be the distribution center. So we have 4 different distribution centers, right? 1, 2, 3, and 4. Okay. And I'm going to put the supply amount in the last column here. And I'm going to put the demand amount in the last row. Yeah. So that's our transportation table. Okay. And in the problem description, the supply amount is how much? It's going to be 12, 17, 11, right? So it's going to be 12, 17, and 11, right? And how about the demand amount? It does say 10 shipments, right? So we have 10, 10, 10, 10 down here, okay? Now we need to determine the unit transportation cost from each source to destinations, okay? Okay, so let's call this is A. No, why don't you just use C sub 1, 1? That'll be more straightforward. So let's call this C sub 1, 1, C sub 1, 2, C sub 1, 3, C sub 1, 4. Likewise, C sub 2, 1, 2, 2, 2, 3, 2, 4, and then C sub 3, 1, 3, 2, 3, 3, and 3, 4. Okay. Okay, then how'd you get C sub 1, 1? According to the problem description here, the freight cost for each shipment is $100 plus 50 cents per miles, right? So the transportation cost should be consist of fixed cost of $100, right? Plus the variable cost, which is 50 cents, right? Times the distance from each source to destinations, right? So we need to use all of these values, right? For computing the transportation cost. So for the C sub 1, we need to use 800 miles. So you need to multiply by 800 up here, right? Then how much is that? So it's going to be 400 plus 100. That's 500, right? So C sub 1 up here has to be 500. Okay. So that's going to be one of the our objective coefficient value, right? Okay, now then similarly, how'd you get C sub 1, 2? Again, we're going to use the same formula. Fixed cost of $100 plus 50 cents times the total mileage from plant number 1 to distribution center number 2, which is 1,300 miles. So from here we have 650, right? Plus 100, that's going to be 750, right? So you should be able to do the rest of them, right? C sub 13 be 100 plus 0.5 times this time 400, right? That's going to be 300. C sub 14 would be 100 plus 0.5 times 700. That's going to be 450, right? Okay, then similarly, anyhow, we need the coefficient, objective coefficient value. So let's do this and complete the computation. C sub 21, 100 times 0.5, I'm sorry, 100 plus 0.5 times 100, 1,100. So that's going to be 650, right? About 6 sub 22, 100 plus 0.5 times 1,400. So that's going to be 100 plus 700, which is 800. C sub 23, 100 plus 400 times 0.5. No, 600 times 0.5, right? Okay, 300 plus 100 is 400, right? And C sub 24, how much is that? 100 plus 0.5 times 1,000, so it's going to be 600, right? Okay, similarly, how about 3-1? Let me just write down. Okay, probably is better. 600 equals 32. 100 plus 0.5, 1,200, right? C is 33, 100 plus 0.5, 800. C is 34, 100 plus 0.5, 900. So how much are they? It's going to be 400 and 700, 500, right? And last one is going to be 550, right? Okay. In a way, you can complete the transportation table, okay? And once you build up this transportation table, the rest of it's very trivial, right? So our LP model would be minimize the total transportation cost, or the total, yeah, in our case, the transportation cost, right? So we are going to use all of these values that we obtained. It's going to be 500, 753, 450. So it's going to be like 500 x11, right? 750 x12, 300 x13, 450 x14, right? Plus all of this, okay. So it's going to be 650 x1, x21, 800 x22, 400 x23, and 600 x24, right? And finally, the shipping cost from plan number 1, right? Goes here. So 400 x31, 700 x32, 500 x33, 550 x34, right? That's our objective function. And transportation problem always has 2 different sets of constraints, right? One is supply constraint, and the other is demand constraint, right? So let's consider the supply constraint first. For the plan number 1, our supplier number 1, how does it look like? It's going to be x11, x12, x13, x14, right? Has to be less than equal to the capacity of plant number 1, right? Which is 12. It's got to be less than equal to 12 shipment, right? For plant number 2, supplier number 2, you're going to have x21, 22, 23, 24, has to be less than equal to 17, right? From here, right? Or up here, 17. Likewise, the third supply constraint, you're going to use right-hand side value of 11 has to be greater than equal to the summation of x variables, x31, 32, 33, and 34. since we have these three suppliers, so we must have three supply constraints. Next, we can move on to the demand constraint. So we are going to have four of them, right? For each distribution center in our cases, right? So the first one should be x11 plus x21 plus x31, right? Has to be greater than equal to the demand amount from the destination number one, from the distribution center number one. Okay. Our second demand constraint would be x12, x22, x32 has to be greater than equal to 10. Likewise, x13, x23, x33 has to be greater than equal to 10 again. And then x14, x24, x34, right? This is x24. Has to be greater than equal to 10. So this is the demand constraint. And this is supply constraint, okay? And don't forget to add sign restriction. X of ij has to be greater than equal to j, equal to 0, sorry, for all I and j values, okay? And I is gonna be 1, 2, 3, right? And j is gonna be 1, 2, 3, and 4 in our case, okay? So this is our complete LP model for our first example problem, okay? Okay, so let's move on to the next example. Okay, so let's read the problem description together. The Bank of Las Cruces has two sites at which checks are processed. And site number one can process 9,000 checks per day, and site number two can process 7,000 checks per day. And the bank processes 3 types of checks, and each day 5 checks of each type must be processed. And the processing cost per check depends on the site at which the check is processed. And the processing costs are summarized in this table. And we are required to determine the linear programming model that can be used to minimize the daily cost of the processing the checks, okay? Okay, now let me insert a new page so that we can work on this new example problem. Okay, so earlier I mentioned that although many applications of the transportation problem somehow involved the determining how to optimally transport the shipments, but some of its important applications actually have nothing to do with the transportation, right? So this would be one of those examples. And in this case, actually, you may consider the 2 processing sites as the sources. and the check types to be the destinations, or vice versa. Okay. So in our transportation model, let's use the processing sites as the sources and the check types as the destinations. Okay. So here, like the previous example, here the processing costs are given. So we can directly use this, right, as the transportation cost for our LP model. So obviously we want to minimize the total processing cost, right? And then let's use 5 cents for X11, right? And then 4 cents for X12. And then here, 2 cents for X13, plus 3X21, 4X22, and 5X23. Okay, so that's our objective function. Pretty simple and straightforward, right? And then how to get the supply constraint in this case? Because in our example, we're going to use these 2 processing center as the sources. And there's 3 different checks types to be the destinations. So the supply constraint in our case going to be X11 plus X12 plus X13, right? Has to be less than or equal to how much? It's going to be 9,000, right? So it's better to complete the transportation table like we did earlier in the previous example. So let's add some necessary information to complete the transportation table. So here, I'm going to put 9,000 and 7,000, right? And down here, I'm going to include 5,000 each. Okay, 5,000 each. So in this case, that's going to be supply amount and demand amount in the last row. Okay. So once you have this complete transportation table, then it's very easy to construct the LP model, right? And our second supply constraint would be X21, 22, 23 has to be less than or equal to 7,000. So our supply constraint has been done, right? Now we need to consider the demand constraint, 1 for each column, right? 1 for each types of checks. So our first demand constraint would be X11 plus X21, right? Has to be greater than or equal to 5,000. X12, X22 has to be greater than or equal to 5,000, right? 1, 3, x 2, 3 has to be greater than equal to 5,000. Right? This is our demand constraint, right? Also adding the sign restriction. All of the decision variable has to be greater than equal to 0, right? For or I equals 1 and 2 and j 1, 2, and 3. Okay, so this is our complete LP model for the second example problem. Okay, so this is all for today, and I will meet you next time. And next time I'm going to talk about the assignment problem. Okay, and probably we're going to have 1 more hour to talk about the transportation and assignment problems before we move to the new topics. Okay. Okay, thank you. I will see you next time. Bye-bye.